Last time we talked about how heat is transferred between a hot object and a cold object, and we said that that anytime there's a temperature change, you can measure how much heat is required to do that using the specific heat equation. Q equals C times M times delta T. Today we're going to talk about something a little different, but also incorporate some of that last lesson. We're going to talk today about what happens when you have something change state from solid to liquid, liquid to gas, or gas to liquid, or from liquid to solid. So the first thing we have to recognize here is this statement right here. It says, at standard pressure, all pure samples of boiling water are what temperature? So if you know the boiling point of water, all samples of pure water, of boiling water, are 100 degrees Celsius. You guys actually saw that in the lab last time. All ice water mixtures, and you didn't see this in the lab before, but they're all 0 degrees Celsius. So why is that? In other words, when you were heating up your metal cube last time, or your metal sample, it pretty much landed right at 100, maybe 100.5 or maybe 99.2 or something, but it pretty much stayed constant once it reached that boiling point. And the reason is the boiling point itself, that phase change process actually involves an energy change. So as I have my temperature rising, and if you look at this graph on the left here, this would be a sample of water going up in temperature from about room temperature, which is down here around 20, all the way up to the boiling point at 100, but then you'll notice the temperature just levels off. So why does it level off? And again, you saw that in the lab last time. Well, it levels off because phase changes themselves involve an exchange of energy. So what we mean by that is essentially that either energy is taken in an endothermic process, or it's given off as an exothermic process. So in the case of boiling water, when you get to the boiling point and you start to see those bubbles, all the energy that the hot plate or stove or whatever it is you're boiling on, all the energy that's being added to that sample of water is being used to separate the water molecules. So you've got these water molecules that are attracted to each other through intermolecular forces, through like hydrogen bonding. We talked about that last semester. And that attraction is difficult to overcome. So all the heat that we're adding once we reach that boiling point, all the heat that we're adding is going towards breaking these molecules apart from each other. And so the temperature doesn't rise because it's all being used for that process. Then once we turn it all to steam, once we get all of it boiled away, we're going to start to see a temperature increase, because once it's all gas, there's no more boiling process that has to happen. So there's nothing to absorb all that energy, so the temperature starts to rise again. The same thing is true of melting. If you have an ice cube and you take it out of the freezer, it's going to be below 0, but within a couple minutes it's probably going to warm up to 0, but then it's going to plateau and not really change temperature very much, because all of the heat that the room is giving to that ice cube is being used to break the hydrogen bonds and allow the water to become liquid and flow. So again, anywhere where you see a plateau on this little graph is where we have a phase change. So in this case we're melting, and then up here we're boiling. So we can say that every sample of water contains contains at least a little liquid has to be between 0 and 100 degrees Celsius. Because as long as there's water there, adding heat, you would stop at 100 because that water has to boil to gas. Or if you were taking away heat, it would stop at 0 because, again, there's another plateau where freezing would occur. All right. So what do the plateaus represent on our heating curve? We just kind of said it. Those are places where there are phase changes. And the slopes would be places where there are simply temperature changes. So if I were to ask you, what part of this curve do we have, 100% liquid? Well, you can see it's labeled right there. It says water. Along this blue part of the curve, it's just liquid. Once we get up to the green part, it's a mixture of water and steam. So that would be like a pot of water on the stove boiling. And then once you've boiled away all that water, and if you continue to heat it, then you're going to have an increase in temperature again. All right. So this heating curve represents a temperature change from negative 20 degrees Celsius all the way up to about 140 degrees Celsius. So it ranges over about 160 degrees Celsius. Not all heating curves are going to vary by or are going to cover that big of a range. So let's see if we can do this. We're going to draw our own heating curve for water being cooled from 85 down to negative 20 degrees Celsius. So the first question we have to ask is, what physical state is water in at 85 degrees Celsius? All right, well, we can look this up in terms of what the boiling point and melting point of water is, or we can just, we can look up here at this graph. We can see that water is a liquid all the way up to 100 and all the way down to 0. So at 85, it would be a liquid, okay? And if it's cooling, that means, of course, the temperature, and temperature is along the y-axis here, and this would just be time along the x. So if it's cooling, it's going to start up here at 85, and it's going to go down in temperature, okay? So, and it's going to go down in temperature until it reaches what temperature? Okay, so you should have said 0, right? And then it's not going to just continue to go down, it's going to plateau because the freezing process is going to release some energy. It's the opposite of melting. So melting absorbs energy, freezing is going to release energy. It's going to be exothermic. Okay? And so we're taking heat away from the water sample, but because it's freezing and giving off some heat, the temperature stays constant. And then it's going to go down another 20 degrees down to minus 20. So that's my heating curve for water being cooled from 85 down to minus 20. Notice it has 3 parts. Okay. Well, what that means, the fact that it has 3 parts, is we could, if we're doing a calculation, we would actually have to do 3 separate calculations, but we'll get to that in a second. How much heat is involved in a phase change? It depends on the type of phase change, and it depends on the substance. Heat of fusion is the amount of heat released as a liquid freezes or absorbed as solid melts. So a question, how much heat is absorbed by 25.6 grams of ice as it melts? So what we're going to do is we are going to use an equation, and it's a different equation. It's not Q equals C times M times delta T. For one thing, there's no temperature change. We're still finding Q because we're looking for heat, right? But this time we're going to say Q is equal to mass times heat of fusion, HFUS, and that heat of fusion is a constant, and it's right over here on this table. So for any substance, I can look up its heat of fusion and find it pretty easily. So this is a pretty simple calculation. It's just the mass times the number from the table. So 25.6 grams of ice melting, if I wanted to know the heat, the Q, I would just say Q equals, my mass is 25.6 grams. My heat of fusion, I just go over to the table, and it looks like the heat of fusion for water is 334. Notice the unit is joules per gram. All right, and then we figure out our answer. And just simple multiplication. So this one is going to end up being 8,550 joules. Okay? Kind of a lot of heat for such a small mass. All right, next question. The next things here says heat of vaporization, HVAP, is the heat released as a gas condenses or absorbed as a liquid vaporizes. So heat of fusion essentially refers to this bottom plateau, melting or freezing. Heat of vaporization refers to this top plateau, which is generally going to be bigger. That's where we have boiling or condensing. Okay, So that equation is going to be just like the previous one. Q equals mass times, only this time it's going to be HVAP, or heat of vaporization. Okay. So how much heat is, the question is how much heat is released as 15.6 grams of ethyl alcohol, which is ethanol, condenses. So you just have to understand that condenses is referring to HVAP rather than H fusion. So we're going to do Q equals 15.6 grams times, and then I go to the table and I find the HVAP for ethanol, which is 879 joules per gram. And of course my answer is going to be in joules. I didn't emphasize canceling units earlier, but that'll be how it works. And I get 13,700 joules. Okay. All right. We'll go over the question about sweat there, the next one, in a little bit, or I'm sorry, in class. Let's go ahead and get down to, and then also the next question about melting silver. We'll do that one in class. Let's talk about combining the heat of fusion, heat of vaporization, and specific heat. So the question I want to do here is, how much heat would be required to raise 200 milliliter sample of water from 50 up to 125 degrees Celsius? The first step is always going to be to draw a heating curve. So at 50 degrees Celsius, I'll just put that down here someplace. Okay, and this is temperature and this is time, always. What physical state would water be in? So between 0 and 100, it would be a liquid, right? So if we add heat to it at this point, the temperature is going to go up, and it's going to go up until it hits the boiling point, right? 100. And then what does it do at the boiling point? It plateaus, right? The temperature does not change while the water is boiling. But once we've boiled all the water into steam, then we can have another increase in temperature. And so it's going to go up to 125 in this case. Okay? So we have those three parts, those three separate things happening. I'm going to label these 1, 2, and 3, and we're going to talk about how we would separately calculate each one of them. All right, so step 1 would be taking the liquid water from 50 up to 100. So for this problem, this is going to be Q equals C times M times delta T. And the reason I know it's this equation is because I have a temperature change. Anytime that we have a slope, in other words, it's not a plateau, we know we're going to be using this equation because we have a delta T. So let's go ahead and plug in the numbers. So C for liquid water, specific heat, 4.18. Okay, my mass in this case, 200 milliliters of water weighs 200 grams. And then don't do the full delta T. In other words, don't go 125 minus 50. We're just talking about step 1. So you would do 100 minus 50. So that is a 50 degrees Celsius temperature change. Okay. And if I multiply that out, I should get about 41,800 joules. Okay. That's the first step. And then the next step, step 2, we have a phase change. So the only question is this vaporization or is this fusion? Okay. Well, if we're at the boiling point, whether we're going up or going down, in this case we're going up, but if we're at the boiling point, it's vaporization. So my equation number 2 is going to be Q equals mass times heat of vaporization. So again, by saying mass, 200 grams, in the heat of vaporization for water, if I go back up to my table, is 2,260 joules per gram. Okay, and then we get 452,000 joules. All right, and then step 3, we're going up in temperature again. So which equation are we going to use if we have a delta T? We're going to use this first equation again, right? So Q equals C times M times delta T. Just be careful. This specific heat for water in this state, which would be a gas because it's above the boiling point, is different from the specific heat of water when it was a liquid. And if you look it up on the table, our specific heat for water as a gas is only 1.87, so it's quite a bit smaller than water as a liquid. So 1.87 joules over grams times degrees Celsius. We're still dealing with 200 grams of it. This time our temperature change is just from 100 up to 125. So that's a 25-degree temperature change. And I plug these in the calculator and I get 9,350 joules. Okay. And the last step, it just wants to know the total heat. The question asks for the total heat. So what I'm going to do is take these three numbers, my three answers, and add them together. All right. And I should get 500 and 3,150 joules. And if I go all the way back up for sig figs, go back to my original question, it had, looks like 3 sig figs. So I'm going to round that. I'm going to say or just 503,000 joules. Okay, and we're going to do those other problems in class. So just make sure that you come to class with these notes that I've given you.